This video is to help you with the data analysis for the addition of forces and simple machines lab. In question 1, we upload a picture of the apparatus showing the water bottle suspended by two springs. To do that, we click on the box, browse to where your image is, stored on your computer, and open it, and it should be uploaded in the box. In the next question, we have to draw a free body diagram of the water bottle showing all the forces acting on the water bottle when it is placed on the digital scales. To do that, let's review what a free body diagram is. First, let me draw something called a space diagram. A space diagram shows what the situation would look like if we took a photograph. These are supposed to be my scales, or rather the digital scales. My water bottle is here. And my spring scale is here. So I'm going to be pulling upwards with a force here. I was labeling my spring scales. So this is what we call a space diagram. It is a sketch of the actual situation. It's pretty similar to what you would get if you took a photograph of the situation. Now what we need to do, we need to draw a free body diagram of a specific object in the space diagram. In this case, the specific object is the water bottle. So what we do, we take the water bottle here and we imagine that we are isolating it. So I'm going to draw a bubble around here, and that is the part of the system I am isolating. I will represent everything inside this green cloud as a single point, because this is a free body diagram of the particle representing the water bottle. By particle we mean something that has no dimensions. It's basically represented by a point. So we've shrunk this into a point, and now we're going to see what forces are acting on it. Well, what does the water bottle feel? It feels its weight, which is, I'm going to represent as W. Actually, I'll just write it in. So it feels its weight pulling downwards. It's got a string here, and that string is providing an upwards force, size P, and the size of P is given by the reading on the spring scale. There's also another force. There is an upwards force from the digital scales. That's called a normal force. And in our free body diagram, we always draw the forces radiating outward, from the particle. So this N here would be the normal force. It's called the normal force because it acts perpendicularly to the surface with which the bottle is in contact with. So normal force. I will give the normal force a symbol like so. Let me just redraw that. So that we do not confuse that with the uppercase N that we use for newtons. So we see that we have two forces acting upwards on the bottle. The upwards force from the platform of the digital scales, the pulling force from the string, and acting downwards, the weight. This normal force can be measured as this is given by the reading on the digital scales. Let's see why that is. If we draw a free body diagram now of the digital scales, so now I'll draw a cloud around the digital scales. What forces does the digital scales feel? Well, it does feel the push of the table. So this is the table pushing upwards on the spring scale. On the digital scales. And then if the water bottle feels an upwards force from the platform of the digital scales, then according to Newton's third law, the digital scales must feel an equal and opposite force from the action of the bottle pushing down on the scales. Okay, so these forces here, this is the normal force on the bottle. What we see here, this is the free body diagram of the digital scales. So the reading on the scale, on the digital scales, is given by this value here, how much the water bottle is pushing down. But that's equal to how much the water bottle is being pushed upwards by the platform of the digital scales. So these are mutual forces of interaction between the bottle and the digital scales. So this is a different way of looking at how the forces are acting. Let's now try and predict what this reading here will be. The way we do that is to realize that the water bottle is in static equilibrium. It is not accelerating up or down. So therefore, the forces on it must be zero. So therefore, if we add the forces acting upwards, P plus N, this force is acting downwards, so we need to subtract that from the total. Let's call this upwards direction the y direction. So we can see that the sum of the forces, this symbol here is sigma, means sum, in the y direction is going to equal this upwards force P. P is positive because it agrees with the positive direction of y, plus this normal force, the push upwards from the digital scales, and then this weight is negative because it's in the opposite direction to the y direction, and all of that must equal 0. So therefore we can see that P plus N must equal W. So P is the reading on the spring scale. So in my case, that was equal, well, in all our cases, that should equal 0.5 newtons. So therefore, 0.5 plus N must equal the weight of the bottle, which was 1 Newton. So therefore we can see from this equation that the normal force must equal 1 minus 0.5, which is equal to 0.5 newtons. So we predict that the size of the normal force on the bottle must be 0.5 newtons. So the 0.5 newtons upward force from the digital scales plus the 0.5 from the pull of the string is sufficient to counteract the 1 Newton weight of the bottle. In question 3, we have to enter in our prediction for the size and normal force on the water bottle from the diagram in part 2 of this analysis, which is the free body diagram. So our result was 0.5. We now need to see how a force downwards of 0.5 on the as experienced by the digital scales, how that would affect the reading. Well, the way the digital scales work is that it senses the weight of the object, which is the force of gravity on it, and then converts that back into what the mass of the object should have been. So in order to convert 0.5 newtons into a mass which should have the equivalent weight as 0.5 newtons, we perform this calculation. So the equivalent mass, m, would equal 0.5 newtons divided by 9.81, which is the acceleration due to gravity, and multiply that by 1000 grams per kilogram to give the answer in grams. So let me just work that out, and the answer to that would be 51 grams. So here you can, that's the theoretical value. And then right next to that, your experimental value. This is the reading that you got on the scales. And let's just say I got 54 grams. We can compare the two and we can determine whether they're reasonably close or maybe they are not particularly close, in which case we can discuss why that might be. Okay, in part 5 we need to draw a free body diagram of the paperclip that connects the 3 strings, the inclined string, the horizontal string and the vertical string, in part 2 of the experiment. So in that case, the paperclip, if we represent that by a particle, a point, there was a downwards force of 1 Newton due to the weight of the water bottle. There was a tension in the string this way, and there was a tension in the string this way. Oh, sorry, let me call this T2. Apologize about that. This tension is the reading on the spring scale when it is placed on the horizontal string. In my case, I got an experimental value of 1 Newton. And for T1, I got 1.5 newtons. And that was my experimental value. So what we had to do actually was to draw the diagram to scale using a scale of 10 centimeters equals 1 newtons and determine the resultant of the horizontal and the vertical forces. If we draw this to scale, then according to Isaac Newton, the addition of those two forces is given by the diagonal of the parallelogram formed by drawing this force and this force as the sides of a rectangle. So if I draw a parallelogram here, And then this diagonal is the resultant of, if we call this the weight, this would be the resultant of T2 and the weight W. So we need a scale diagram. So let me switch or insert here a piece of graph paper. Okay, so the first thing is I'm going to draw the weight. Here I'm using a scale based upon the squares on my grid. So I'm saying 1 square here is equal to 0.1 newtons. You can do a similar thing. I've suggested that you draw a scale of 1 centimeter equals 1 newton. You don't have to do that if you have some paper with an existing grid. So this is drawn to scale and it is 10 squares long. And this represents a downwards force of 1 newton. The reading on my spring scale when placed on the horizontal string was also 1 newton. So I have drawn this line 10 squares long. I'm now drawing a dotted line that is parallel to the vertical line here, and I'm going to draw another dotted line that is parallel to the force drawn at the top, the horizontal force. When I draw these dotted lines, we see the outline of a rectangle. Had these forces been at an angle, we would have got a parallelogram. The resultant is the diagonal of this rectangle that we have drawn. So I'm going to draw the diagonal. Please use a ruler when you do that. Now I can use a ruler to measure how long this line is and express that in terms of the scale. To do that, use a ruler or tear off a piece of your squared paper to determine the length of the resultant line that we've just drawn. So here I've copied and pasted some of the grid so I can determine the length. And the length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is 14 squares long. And that's equivalent to 1.4 newtons. So the resultant of the horizontal force and the weight of the water bottle is equivalent to a 1.4 newton force acting 45 degrees below the horizontal. The force in the angled string, should be equal and opposite to the resultant of these two forces in order to balance them out. So we can compare this value with the value that we obtained on the spring scale when it was attached to the angled string. So just to clarify, the angled string will be like so, and that's represented by T1 in our previous diagram. And what we've done, we replaced the two forces by a single 1.4 Newton resultant. So we see that these two forces must be equal and opposite in order for the paperclip to be in static equilibrium. So that's how we answer this part of the question. You may have to insert an extra page in order to do that. So in part 6 it says the resultant of the horizontal and vertical forces should be equal to the tension in the inclined string. Compare your calculated result to the measured tension. So here we can indicate our calculated result was equal to 1.4 newtons, and our measured result in my case it was 1.5. And now we can ask ourselves, do these agree well enough such that the parallelogram method of vector addition is verified? In my case, I think within experimental error, due to the accuracy of the spring scale, the results do agree in a way that we can see that there may be some usefulness to the parallelogram method of vector addition. Okay, in part 7 of this analysis, we go back to part 4 of the experiment, which is the simple pulley system. And we calculate the average of the force readings to just get the bottle moving upwards and the force required to allow the bottle to begin falling. Averaging the results helps to account for friction in the pulley. In my case, to get the average here, I had 1 Newton force to allow the bottle to start falling. No, actually it was less than that. 1.5 was required to get the bottle moving upwards. 0.5 was required to get the bottle falling. Divide that by 2 and we can see that equals 1 Newton. So in part 9, so according to, actually I've numbered the parts wrongly, sorry about that, should have been part 8. According to Newton's laws, the tension is a rope that is the tension of a rope, is not changed as it goes around a light frictionless pulley. Do your results support that theoretical prediction? Well, we expect the tension. Let me draw another diagram to illustrate this. If we have our pulley here, we are pulling down with a force and we have a weight attached here. If I draw a free body diagram of the weight, this is an acronym for free body diagram, FBD. This is the action of gravity on the weight pulling downwards, and upwards is the tension in the string. So this tension, so we can see that these two forces need to balance out. So therefore the tension is equal to the weight of the water bottle. Now, if the tension in the string is unchanged as it wraps around the pulley, then we expect P to be equal to the weight of the water bottle. P is the reading on the spring scale. Okay, the weight of the water bottle. But because of friction, it will not exactly equal that. But we can average out for friction by using the method that I just described. So to answer the question here, we can compare the tension, the average tension in the string that we got here, with the weight of the water bottle. In the next part, so this, I will renumber this, so this is actually part 8, and this will now be part 9. Mechanical advantage. So this is a concept to do with machines. It's equal to the ratio of the load, so this is the weight or the force that we're trying to move, to the force applied to move that load. So what a machine does is convert a small force applied over a larger distance into a large force which is applied over a short distance. This is very useful as it allows us to basically apply larger force to something with a very little input force. The ratio of the load to the input force is called mechanical advantage. It tells us how many times our machine is multiplying our input force. In our case, the input force is the average reading on the spring scale, and the output or the load is the weight of the water bottle. For the simple fixed pulley, we typically get a mechanical ratio of 1 to 1. So that's the expected value. And you can calculate the mechanical advantage of your system by dividing your result to this part by the weight of the water bottle. Now, for the moving pulley system, we need to calculate the average of the force readings to just get the bottle moving upwards, and the force required to allow the bottle to begin falling. In my case, that was about 0.6 newtons. So we see we needed less. Hopefully you will see that you need less force to pull the bottle upwards when we use the moving single pulley system rather than the simple fixed pulley system. In this case, the mechanical advantage, the theoretical mechanical advantage, is actually going to be 2, but because of the weight of our pulley, we'll have some variation from that. So our experimental value will be 1 over 0.6 in my case. You may get a different value over here. And so that value is 1.67. So you can, in the last part, so this is part 11, so I have messed up the numbering, I will fix that. In the last part we can comment on the usefulness of the system using the moving single pulley. And before we leave that, I just want to discuss how that single moving pulley system works. The way it works is if we have a pulley and we have the string wrapped around like so, and this is attached to a fixed object, and we put our weight here, you will see that there are 2 tensions pulling upwards on this pulley, which is supporting a weight acting downwards. So therefore, in order for this to be in equilibrium, 2 tensions must equal the weight. So therefore the tension in the strings must equal weight over 2. This is assuming there's no friction and that the weight of the pulley is 0. Okay? So this is assuming a light, frictionless pulley. In our case, the pulley is neither light compared to the weight of the water bottle, and it's not frictionless. So we'll get some variations from this, but we expect the tension to be around half the weight of the weight applied to the pulley. In our case, that's 1 Newton. In such case, the theoretical mechanical advantage would be 2. See, the pulling force here will be required to generate the tension, and this P will be the reading on the spring scale. So I hope that helps in completing the data analysis for this experiment.